Hello everyone. So in this video we're just going to be wrapping up performance issues, and I'm just going to be solving one of the exam questions. So this is a question from our exam, and I'm just going to be showing you how to go about solving it. Okay, so ignore this. The question is: suppose a program takes 100,000 instructions to run on a 40 megahertz single processor with the following instruction type mix. So for CPI for each. So then we have instruction. So we have the instruction type, instruction count, and then CPI. So integer type 45,001, data load 32,002, floating type 15,002, control 8,000, and then 2 there, right? So the first part of the question is determine the CPI, right? Determine the execution time. So now, if you remember, execution time, capital T, is equal to our instruction count times our CPI, right? Our CPI. Remember, this is our average CPI, right? Our average CPI times the period. That's the symbol there. So first thing we're going to do is that we're going to find our average CPI. So our CPI average there. This is going to equal. So remember the formula for CPI, right? So this is going to be 45,000 over 100,000, which is just 0.5, right? I could write 45,000 over 1,000 times 1, then 32,000 over 100,000, but we can just do that in our head, it's fine. So I'm going to do 45,000 divided by 100,000, which is 0.45, right? Times our CPI of 1 plus 32,000 divided by 100,000, which is 0.32 times 2, plus 15,000 divided by 1,000, which is 0.15 times 2, plus, then this would be 0.08 times 2, right, like that there. If I then calculate all this on my calculator, the answer should be 1.55, right? So this is our CPI, right? This is our average CPI. Okay, then now we go to our next page. Okay, then now what are we going to do? We're going to calculate our time, right? Time being equal to our instruction count times our CPI there, average, CPI average there, times our period there. This is then 100,000 times 1.55, and then times, now this is why I said ignore this part, but 40 megahertz, remember our the frequency we need to use should be in hertz, but this is megahertz. And what you know is that hertz is basically times 10 to the power 6. So mega, if you remember the conversions, you have hertz, then kilohertz times 1000, which is the power 3, then megahertz, which is the power 6. So 10 to the power 6 here, like that. So 40 times 10 to the power 6, which if we get that 0 there, it just gives us 40 times 10 to the power 7 hertz there, right? So times 1 over 40 times 10 to the power 7 hertz, right? So we have that there. And then if we then go in and punch this on our calculator, we're going to have 100,000 times 1.55, right? Then all of this times 1 over, open brackets, 40 times 10 to the power 7, right? Which gives us it's 1 over 8000, which if we leave it in our decimal should be 0.0038875 seconds. So this is our execution time for this question, right? So this is the first part of the question, and in the exam that was like 5 marks. Next is the MIPS for the processor, right? What is the MIPS for our processor in this case? Okay, so remember MIPS has a few formula that we can use. So this is our second question. So MIPS is equal to our instruction count over our period times 10 to the power 6, which is same as using our frequency over CPI. Oh, this is our execution time, CPI times 10 to the power 6. You just need to remember one of these formulas. In this case, I'm going to use this one, right? And you can also try proving it using this other formula here. Then what I'm going to do is that I'm just going to say, this is, what's our frequency? It's 4 times 10 to the power 7, 10 to the power 7, over what was our CPI? 1.55 times 10 to the power 6. which if we then punch this on our calculator, 4 times 10 to the power 7, right? Then divide this by 1.55 times 10 to the power 6, which gives us 25.8064. So if you punch that on the calculator, you get like 25.8645161, something like this. This is the answer you should get from the calculator, and that's how we calculate MIPS there. You can try using the other formula. So it would be 100,000, right? 100,000 divided by, what was our time? Our time was 0.00387 times 10 to the power 6, which would also give us the same thing. So if we use this time that we found here, which is in this place, again, you still get the same answer. So again, when it comes to MIPS rate, it's about which one you remember for the most part, because there are two formulas. Okay. Next part, what is the speed up on a 10 CPU system if 20% of the code can be perfectly parallelized? So this is where we use Amdahl's law, right? This is where we use Amdahl's law, where we have speed up, or something that's SU is equal to 1 over 1 minus f plus f over n there, n being the number of CPUs that we have. In this case, our f is equal to 0.2 because it's 20%, and 20% of 1 is just 0.2. Okay, so then we're going to have 1 over 1 minus 0.2 plus 0.2 over our 10 there, which will then, if we punch this on our calculator, we're going to have 0.8, right, plus 0.2 divided by 10 like that. Then we're going to have 1 divided by this answer, which is 1.2195. 1295, and given this pattern, I'm pretty sure it just keeps on going like that. But yeah, so this is our answer, which is just the same as 1 and 9 over 41. Yeah, if you want to keep it in that form, but just leave it like this is just decimal, not as a fraction. But this fraction, we're going to use it for the next calculation. Okay, so what is the last part of this question, right? Last part is determine the execution time for the program after the speed up, right? So now here's something you need to remember. I think something you need to remember when it comes to this. When we have our speed up, right? When we have our speed up there, what happens is that if speed up goes up, our execution time must go down, right? So if you see here, our speed up is greater than 1, right? So mean our execution time will go down. And how do you calculate this? Well, all you need to know is that our new time is just equal to our original time divided by our speed up. Just what you need to remember, right? It's just what you know. Of course, they're inversely proportional to each other. As one goes up, the other must come down. Is it right? So meaning, so you might imagine a question where you might say, okay, initially we ran this code on a CPU with like 5 cores, and then we ended up running it again on a CPU with 2 cores. Meaning, of course, that might the ratio there might go down, right? I was looking for another question similar to that. I think I remember solving something like that once, if I'm not mistaken. But yeah, so all we need to do here is just say what is our original time. So that's 0.003875, right? Divided by what's our speed up, 1.2195. What is 195. 1295, and it keeps on going like that. But since I already have that value on the calculator, I'm just going to use the fraction that we have there. So it's going to be 0.003875 divided by the previous answer we got for the speed up, which gives us 0.00317775 seconds. And this makes sense. Our speed up is greater than 1, so we did increase our speed somehow, meaning our new time should be less than our original time. So this is how you go about solving questions for basically performance issues questions, right? So this is a full exam question. This is how it came for us in our exam. So yeah, if you have any other questions, of course, just feel free to ask. But for now, we're going to say bye to this topic.